So in the last class we discussed a divide and conquer algorithm to multiply two large integers each containing n digits. So for example, if you are given two n-digit integers, say x and y, okay, we can partition the digits into equal half, provided n is of the form 2 power k. Then x can be represented as xl into 10 power n by 2 plus xr. Similarly, y can be represented as yl into 10 power n by 2 plus yr. Okay, now if we multiply xy using normal method, so xy is xl yl this thing. So equation 1 we get. Here xl yl, it is n by 2 digit multiplication. xl yr is also n by 2 digit multiplication. xr yl is also n by 2 digit multiplication. xr yr also n by 2 digit multiplication. Okay. So based on this, we will get t of n as 4 times t of n by 2 plus. After that, we need to multiply xl yl with 10 power n. This we can do it in theta of n time. Similarly, this we need to multiply with 10 power n by 2. This also we can do it theta of n time. After that, combining the results, that is finding the sum, that also we can do it in theta of n time. So entire thing we can put it as theta of n. So the recurrence relation is t of n is 4 times t of n by 2 plus theta of n. So by case 1 of master theorem, it is same as theta of n square. So here we have applied divide and conquer, but we could not get any advantage over classical method. Even classical method also, it is same as classical method or traditional method which we use for multiplication. It is also same as theta of n square. So there is no advantage. There is no advantage. Then how to get another divide and conquer algorithm to solve this problem with better running time than classical method. With better running time than classical method. How to do it? How to do it? Somehow, if we can ensure that, is it possible to multiply two n-digit numbers in less than n time? X and y n digits. Is it possible to find xy in little o of n time? Is it possible? Is it possible to find xy in little o of n time? Is it possible to find the product xy in little o of n time? That means less than n time. Less than n time, is it possible? It is impossible. Why? Because there are n digits. That n digits is scanning itself. That itself takes minimum n time. Okay. So less than n time, it is impossible. Any algorithm to solve this problem, it takes at least n time. At least n time. So now next question is it possible to get an algorithm which is better than this divide and conquer algorithm? One is similar to Stressen's method. Here also, if we can ensure that number of sub-problems we are solving, if it is smaller than 4, that is, say, for example, 3, that is 3, then what is the time it takes? What is the time it takes? Which case is applicable here? Which case is applicable? Which case of master theorem is applicable? Case 1. By case 1 of master theorem, it becomes theta of n power log 3 base 2. N power log 3 base 2, which is same as theta of approximately n power 1.585 approximately. It is smaller than n square or not? It is smaller than n square. Yes. Then how to do it? Idea is very simple. How to do it? Now look at equation 1. Equation 1, we are calculating xl-yr plus xr-yl. Now the question is it possible to calculate this product xl-yr plus xr-yl easily? Here actually we are performing two multiplications, no? xl-yr, xr-yl. Is it possible to calculate this value easily? That is the idea. Idea is very simple. So what is xl plus xr into yl plus yr? This can be written as XLYL plus XLYR plus XRYL plus XRYR. Is that correct? What are XRYL? It is clear to us. This is leftmost n by 2 digits, rightmost n by 2 digits in X, similarly in Y. Now we are actually looking for this value. Now tell me what is XLYR plus XRYL? It can be written as XL plus XR into YL plus YR minus these two terms, we move it other side. XLYL minus XRYR. Is that correct? Is that correct? Is that correct? Now what is that we do is, instead of XLYR plus XRYL, we substitute this value in equation 1. This value instead of XL plus instead of this value, we substitute right hand side value in equation 1. What is our equation 1? What is our equation 1? What is our equation 1? XY equal to XLYL 10 power n plus XLYR plus XRYL times 10 power n by 2 plus XRYR. No, this is our equation 1. Substitute 2 in 1. 2 in 1. What is that we get? What is that we get? What is that we get? XY equals to XLYL 10 power n plus, now in place of this we are going to substitute this value equation. Okay, so what is that? What is that? What is that we get? XL plus XR into YL plus YR minus XLYL minus XRYR. This is the value we are going to substitute. Already 10 power n by 2 is there. Plus XRYR. Now if we calculate product based on equation 3 instead of equation 1, then what happens? Then what happens? Then what happens? So now we are going to calculate product XY using equation 3. Calculate XY using equation 3. Equation 3. If we calculate it using equation 3, then what is Tn? What is total time this algorithm takes? XLYL we need to calculate how much time it takes. Calculation of XLYL. How much time it takes? Calculation of XLYL, how much time it takes? How many digits are there in Excel? N by 2. How many digits are there in YL? N by 2. So X, if there are n digits, in both the integers have n digits, time is T of n. If there are n by 2 digits, T of n by 2. What is time for the XR YR? T of n by 2. In our Excel YL, XR, YR, we have already calculated. We can reuse the result without calculating again. XL, YL, XR, YR, we can reuse the result. Now, what is XL plus XR into YL plus YR? What is the size of this? How many digits does it contain? Number of digits? Number of digits in XL plus XR? How many digits XL plus XR contains? How many digits XL plus XR contains? Sum of two four-digit numbers. For example, say X contains 8 digits. 8 digits. Now, how many digits XL contains? 4. XR 4 digits. Okay. Now, if we add any two 4-digit integers, what is the integer that we get? If we add any two 4-digit integers, what is the integer that we get? If we add any two 4-digit integers, what is the integer that we get?
Maximum 5 digits we may get, sir.
Thank you, ma'am. So maximum 5 digit, either 4-digit integer we get, definitely not 3-digit integer or 5-digit integer. So is n by 2 digit is n by 2 or n by 2 plus 1? N by 2 or n by 2 plus 1. So similarly, what is number of digits here? Number of digits in YL plus YR is n by 2 or n by 2 plus 1. Is that okay? Is that okay? So now tell me what is reconciliation for T of n? What is reconciliation? What is T of n? What is T of n? Okay, let us assume both as n by 2. Okay, both as n by 2. Assume that this is correct. And then what is reconciliation? First one is T of n by 2 time plus. What about second multiplication?
Again T of n by 2.
T of n by 2. Other case we'll discuss. First to n by 2 case we'll consider n by 2 plus. What about this? What about this XR YR multiplication? That is also T of n by 2 plus remaining work similar to previous case example 1 here also equation 1 here also we can do it in theta of n time. And okay, no? So that means T of n is 3 times T of n by 2 plus theta of n if n is greater than or equal to 2 and T of 1 is 1 constant. 1 digit means directly we multiply. So now which case of master theorem is applicable? Case 1. What is answer? What is answer? Is that okay? Is that correct? Is that correct? Okay. So now, what about this case? Even if we consider this, in that case, we can write it as that is 2 times T of n by 2 plus T of n by 2 plus 1 plus theta of n. Is that correct? Is that correct? If we consider n by 2 plus 1, number of digits in this, no, n by 2 plus 1, this becomes n by 2 digit, n by 2 plus 1 digit multiplication. So T of n by 2 plus 1. Even here also we can show that it is less than or equal to this. So we can show that it is n power log 3 base 2. N power log 3 base 2. So whatever calculation I have done, everything is with the assumption that n is of the form 2 power k. N is of the form 2 power k. So here also same running time, n power log 3 base 2, n power 1.585. It is very much better than traditional method n square. And this is known as Karatsuba's matrix multiplication, large integer multiplication. This is called Karatsuba's. This is whatever based on equation 3, no? Equation 3. So this is called Karatsuba's large integer multiplication. Is that okay? Is there any doubt? But exact reconciliation, if n is not of the form 2 power k, then what to do? If n is not of the form 2 power k, then what to do? Number of digits is not of the form 2 power k. Then what to do? One is 325, the other one is 8769. Then what to do? How to multiply this? Simply, we can append the zeros this side, no? Left side. Value, there is no change. No change. Now we follow the same procedure. If n equal to 13, how many digits, how many zeros we append? If it contains only 13 digits, how many zeros we append?
2 zeros.
3 zeros. To make it exactly of the form 2 power 4, no? N has 13 digits.
13. Okay.
13, 1, 3, 13. Okay, then 3 digits if you append, already 13 digits are there here. So total it becomes 16 digits. It is of the form 2 power k. Again, we follow the same. Is that okay? So in that case, XL and XR, there is difference, no? The number of digits it may have is something less, no? Something less. Okay. In that case, what to do? In that case, what is the reconciliation? Okay, I just give you the reconciliation. The exact reconciliation we get can be written as T of ceiling of n by 2 plus T of floor of n by 2 plus T of ceiling of n by 2 plus 1. We can write it like this. Even in this case also, T of n becomes n power log 3 base 2. N power log 3 base 2. Is that clear? Is that clear? This is exact reconciliation, but even if you understand this, this is fine. Okay. It's better than traditional method. This is known as easy to divide and conquer method or not? Easy to divide, Karatsuba's large integer multiplication, easy to divide and conquer method or not? Does it follow divide and conquer strategy or not? Large integer multiplication. This is also divide and conquer, no? This is also divide and conquer. Okay, one simple question. We have two integers x and y. X has n digits. Y has m digits. Y has m digits. Where m is smaller than square root of n. M is smaller than square root of n. Now you tell me whether classical method is better. Classical method is better or Karatsuba's method is better. We have say simple question. We have two integers x and y. X has n digits. Y has m digits, but m is lower than square root of n. In this case, which method is better?
Classical method is better, sir, because we have to append many zeros to m.
Correct, sir. Your answer is correct. So if you go by, thank you, sir. If you go by classical method, what is the time we require? What is the time we require if you go by classical method? One has m digits, other one has n digits. So classical method, how many multiplications we require? Total?
Mn.
Mn. Theta of Mn. Same thing if you go by Karatsuba, how many multiplications are required? How many multiplications are required? Because one has m digits, no, other one has n digits. So how many zeros we append? Y side, this is y, m digits are there. How many zeros we append? N minus m zeros. Okay, even if I assume that n is of the form 2 power k here. Is that okay? N minus m zeros we append, then we calculate. Then what is the time Karatsuba's method takes? Theta of n power 1.585. Is that correct? Now, what is the value of m? M is less than root n, no? M is less than root n means it is less than m is m plus root n. This is n, no? So it is less than n power 1.5, no? Okay, or exactly you take m equal to root 10. M equal to root 10. Then it becomes how much? This side it is n power 1.5. This side it is n power 1.585. So which is better? Which is better? Which is better? Classical method only is better. Wherever order of growth is less, that is better. So classical method is better. If m is less than root n, definitely classical method only. M equal to root n itself, this one means m less than root n also classical method, no? Okay. So that is about large integer multiplication algorithm. Next problem, the last divide and conquer problem which we are considering is selection problem. So all of us know what is selection problem. What is selection problem? What is selection problem? Finding. This already we discussed. Okay, finding ith smallest element of given sequence or array of n distinct elements. Finding ith smallest element. I equal to 1, it is called minimum. I equal to n, it is called maximum. I equal to n by 2, it is called
median.
I equal to n by 2.
It is median.
Median. Okay, let us commonly put this. Ceiling means whether it is even or odd, it takes care, no? This we call it as median. Okay. Now the question is, how to solve if I equal to 1, that is finding minimum. So what is the algorithm to find minimum of n elements? What is the algorithm to find minimum of n elements? What is algorithm? First one we can say it as minimum. Minimum equal to a of 1. We keep comparing with 2 to last element. Keep updating minimum. Correct, no? Do you remember this we discussed, no, when we talked about selection sort? Is this correct? Is this correct or not? So how many comparisons we are performing here in order to find minimum? How many comparisons?
N minus 1. N minus
Thank
1.
you. Number of comparisons? N minus 1. Number of comparisons is N minus 1. Okay. That means what is the time this algorithm takes? What is the time this algorithm takes? Theta of n. Is that correct? Same thing if I equal to n maximum. Is it possible to do it in theta of n time? Is it possible to do it in theta of n time? Is it possible to do it in theta of n time or not?
Yes, sir, we can.
Same algorithm.
Instead of less than, yeah.
Less than, if you go to greater than, automatically same thing works. No, so it's same thing. It works. So that means how many comparisons? Here also n minus 1 comparisons. N minus 1 comparisons. Now, if we want to find second smallest element, I equal to 2, how many comparisons are required? First, we are given n elements. So one way of doing is find the minimum. Okay, then remove minimum. Remove minimum. Same thing we have done now in selection sort. Next, remaining n minus 1 elements. Again, find the minimum. Is this correct? Is that correct? So, for example, if we are given 10, 2, 5, 30, 4 like this. So 5 elements are given. So first to find first minimum. What is first minimum? 2. In order to find this, how many comparisons we require? How many comparisons we require? How many comparisons we require?
N 4 comparisons.
4 comparisons. So find minimum here, 4 comparisons. After doing this, in general, it is n minus 1 comparisons. After doing this, after removing this, again remaining elements, what is that we need to find? What is that we need to find?
Yes, second minimum.
Now,
Yeah.
remaining elements are 10, 5, 34. Now again find minimum. What is minimum here?
5.
What is minimum here?
4.
4. We return it as answer. So 4 is our answer. Second time, how many comparisons are required? Second time, how many comparisons are required? If there are n minus 1 elements, how many comparisons are required?
3 comparisons. N minus 2.
3, n minus 2. So here n minus 2 comparisons. So total, how many comparisons? If we start with n elements, first to n minus 1, next to n minus 2, that is 2n minus 3 comparisons, we can do it or not? 2n minus 3 comparisons, is it possible or not? Yes. That means using 2n minus, that means what is the time this algorithm takes? Is it theta of n time or not? Theta of n time or not? Similarly, if n equal to I equal to 3, how many comparisons we require? Same procedure. First n elements, find minimum, n minus 1 comparisons. Remaining n minus 1 elements, find minimum, n minus 2 comparisons. Remaining n minus 3 elements, find minimum. Remaining n minus 2 elements, find minimum, n minus 3 comparisons. Is that okay? 3n minus 6 comparisons, is it possible to find the third smallest or not? This is minimum of n elements. This is minimum of n minus 1 elements. This is minimum of n minus 2 elements. Is it clear? Is that clear? Is that clear?
Yes, sir. Yes.
Okay. Now I equal to 4. If you want to do it for I equal to 4, is it possible to do it in theta of n time? I equal to 4. First n minus 1 comparisons, next n minus 2, next n minus 3, next n minus 4. What is this value? 4n minus
10.
What this is sum of this 4n minus 10. Is it theta of n or not?
Yes.
Yes. If I equal to 5, what is the answer? Can you generalize and tell me? Okay, I equal 5 also, I'll write next value I'll ask. Is that correct? I equal 5. If I equal 100, I equal 100. How many comparisons?
100 n, 100 I.
Yes, sir. Up 100 n minus 100 n only, not I.
Sorry.
100 n minus. Okay, this if you simplify, then automatically it is theta of n. No, this part is constant anyhow. It is theta of n or not. Is that correct? Is that correct? Is that correct or not? If I equal to 1000, again is it theta of n or not? If I equal to n, if I equal to n, nth smallest element, which is same as maximum, how many comparisons we require? Can we do it using n minus 1 comparisons? Nth smallest element is same as maximum element, no? Nth smallest element is same as maximum. Is that okay? Nth smallest element means that is largest element, no? Here, what is fifth smallest element here? What is fifth smallest element?
Smallest element.
That is 20.
Yeah,
Which is
it's
nothing
20.
but largest element or maximum element, no?
Yes.
Okay. So if I equal to n minus 1, it is second maximum. This also how many comparisons? First maximum you find, after that second maximum, again remaining elements maximum. This also theta of n. Similarly, I equal to n minus 2, third maximum. N minus 1 plus n minus 2 plus n minus 3. This also we can do it in theta of n time. If I equal to n minus 100, n minus 100, This is nothing but 101th maximum, no? N minus 1 plus n minus 2 plus and so on n minus 101. This will be 101 n minus 1 plus 2 plus and so on 101. This is also theta of n. Are you following? Are you following? Are any confusion here? Is that correct? Now the question is, if I equal to n by 2, if the same procedure if we follow, then how many comparisons are required? N by 2 to smallest element, which is nothing but median. So first one, n minus 1, next n minus 2, plus and so on. That means top procedure. Whatever procedure we followed here, I am going to follow here. So it becomes n I equal to 100 means up to n minus 100. Here I equal to n by 2 means up to n minus n by 2. Is that correct? It is how many times n by 2? Is this correct? N is how many terms are there? 1, 2, and so on up to n by 2. So n into n by 2 minus 1 plus 2 plus and so on plus n by 2. What is that? It takes theta of n squared. Same algorithm. For some values of I, it is theta of n, but some values it is taking theta of n squared time. That means in general, what is the time it takes? Even if I give I equal to n by 4, what is the time it takes? What is the time it takes? What is time it takes? Okay, this also can simplify. This is also theta of n squared. For some values of I, it is theta of n squared. For some values of I, it is theta of n. That means in general, worst case, what is the time it takes? What is the time it takes? What is the time it takes?
Theta of
Theta
n
of n
square.
squared. Now the question is it possible to solve this selection problem? That is finding ith smallest element in little o of n squared time. That is strictly less than n squared time for any value of I. Is it possible to solve it in less than n squared time for any value of I? What does ith smallest element mean? What is its sorted order? This is sorted order, no? This is first position, second position, third position, fourth position, fifth position. That means after sorting the element at first position is first smallest element. Element at second position is second smallest element. Element at third position is third smallest element. Fourth position is fourth smallest element. Fifth position is fifth smallest element. And so on, nth position is nth smallest element, no? Now based on this, can you give an algorithm which is better than m squared? Simply sort given n elements by applying say merge sort. What is the time it takes? What is the time it takes? theta of n log n time. After that, you return give element at the ith position, a of I. Over now. What is time it takes? Giving element at a of I, it is theta of 1 time. So what is the total time? What is total time? For any value of I, what is the total time it takes? What is total time it takes? Ith smallest element, finding ith smallest element. Sorting the elements using merge sort or heap sort also n log n time. Okay, you sort the element using merge sort, that is n log n time. After that, element at ith position is our answer. So what is the total time here? N log n only, which is very much better than n square. Next question is it possible to solve this problem in less than n log n time? That is little o of n log n time. Little o of n log n time. Is it possible or not? Yes, there is an algorithm which solves this problem in order of n time. It is a divide and conquer algorithm. And the name of that algorithm is selection in worst case linear time. Selection in worst case linear time. In the worst case also it is linear. Linear means order of n. Linear time algorithm. Okay, this I am not going to discuss. This is also known as median of medians algorithm. Median of medians. So it is only order of n time algorithm. Is it possible to do better than this? Is it possible to do in better than n time? It is impossible. If there are n elements, we need to see what are the all n elements. No, that itself takes n time. So there exists a best algorithm which takes only order of n time to find any ith smallest element. Ith smallest element. And this is very important algorithm, and it is used as subroutine in solving many other problems. Yeah. Okay, now it is used as a subroutine in solving many other problems. Okay. Okay. So now let us move to other topic. All of us know what is Fibonacci sequence. This sequence is Fibonacci sequence. And what is nth term in the Fibonacci sequence? F of n. What is f of n? F of n minus 1 plus f of n minus 2. Okay, now previous two terms sum. F of 0 equal 0 and f of 1 equal to 1. We have also derived formula for f of n. Now what is f of n? Direct formula for f of n. We remember we solved now when we talked about analysis of recursive algorithm.
Using golden ratio.
This is golden ratio. That is using a characteristic equation method, recurrence relation solving. We got this answer. No, this is known as nth Fibonacci number. Nth Fibonacci number. So based on this, can we write a recursive algorithm to find nth Fibonacci number? Can you give recursive algorithm based on this recurrence relation? Easily we can give, no? And that recursive algorithm is here. This also we discussed, no? Recursive algorithm for computing nth Fibonacci number. This is recursive algorithm. And we shown that this is 1 plus root 5 by 2 whole power n. T of n is 1 plus root 5 by 2 whole power n. Correct, no? So we can say that the of n plus root 5 by 2 whole power n. Is that correct? This also we discussed when we talked about analysis of recursive algorithms. Analysis of recursive algorithms. Now the question is, in this problem, if we want to calculate, say, Fibonacci of n equal to, say, 4. if n equal to 4 is supplied as input. Okay, no? Then what are the recursive calls it makes? N equal 0 or 1, so condition fails. So it comes to this else part. Else part first this call is executed. That means it calls Fibonacci of 4 minus 1. Is that correct? Again, the same call, it invokes the same call. That means n becomes 3. And what is the call it makes? Which is same as 3. What is the call it makes? Fibonacci of 2. Is that correct? And what is the call it makes? Is that okay? Again, what is the next call? I hope all of you know this, no? 0. What is the next call? What is the next call? What is the next call?
No. Yeah, it goes away.
Okay, 1. So what is the next call here? What is the next call? Fibonacci 1 means directly we get answers here. No, that's why I have not written recursive call here. Directly we get 1 here, 0 here, 1 here, 1 here, 0, and here call is Fibonacci of 0. Is that correct? Instead of that, if we are given n equal 5, then it becomes Fibonacci of 5. This side it will be Fibonacci of 3. This 3 again it will be Fibonacci of 2. This side it will be Fibonacci of 1. This side again it will be Fibonacci of 1. This will be Fibonacci of 0. Is that correct? Is that correct? So what is that I have drawn here? It is 3 of recursive calls made when n equal 5. This is 3 of recursive calls made when n equal 5. Is that correct? Now, if you look at this, in order to solve a problem for n equal to 5, it is solving this subproblem, no, where n equal to 2. Is it solving the subproblem Fibonacci of 2? Is it solving Fibonacci of 2? Here also it is solving Fibonacci of 2. Even here also it is solving Fibonacci of 2. That means same subproblem it is solving again and again. Same subproblem is solved multiple times. Means greater than or equal to 2 times. Is this correct? This is one observation. By this is 3 of recursive calls made. Figure is 3 of recursive calls. Recursive calls when n equal to 5. Is that correct? Same subproblem is solved multiple times, again and again. Solved multiple times means again and again. Similarly, if you look at Fibonacci of 3, here also we are solving Fibonacci of 3. Here also we are solving Fibonacci of 3. Even this is also solved multiple times. Okay, now same subproblems here it is solved multiple times. Is that correct? Now, in this entire recursion tree, what are distinct subproblems? What are distinct subproblems? In this entire recursion tree, what are distinct subproblems? What are distinct subproblems? What are subproblems which are present here, which are distinct without repetition? One is Fibonacci of 5. This is same as original problem. What is next? We also have
4, 3, 2, 1.
Fibonacci of 4. We also have Fibonacci of 3. We also have Fibonacci of 2. We also have Fibonacci of 1. We also have Fibonacci of 0. Is that correct? So that means number of distinct subproblems possible in this case, in this according to the recursion tree as well as the recursive function which is given here, okay, is only 6 different subproblems, no? 6 different. So total 1, 2, 3, 4, 5, 6. Only 6 different subproblems are there. But how many subproblems we are solving here? It is definitely more than 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is that correct? 15. 15 or 14, something like that. It is more than 6 or not? More than 6 or not? Recursion tree contains more than 6 subproblems or not? Recursion tree contains more than 6 subproblems or not? Yes, it contains more than 6 subproblems. That means once we know number of distinct subproblems, and if we draw tree of recursive calls made, if the tree contains more than the number of distinct subproblems, okay, distinct subproblems, that means what? There is something which is repeated, no? Some subproblems are repeated, they are occurring again and again, we are solving again and again. Does it imply that or not? Does it imply that or not? Is that correct? This type of subproblems we call it as overlapping subproblems. This type of subproblems we call it as overlapping subproblems. Are there any overlapping subproblems in this case? Are there any overlapping subproblems in this case? Are there any overlapping subproblems in this case? Whether it generates any overlapping subproblems or not?
Yes, sir.
Yes, yes. Next question that comes to natural question that comes to our mind is, why should I solve the same subproblem again and again? Only once I solve, okay? And whenever I encounter the same subproblem, that answer we reuse that answer. Why should we solve the same subproblem again and again? Only once we solve. Whenever we encounter the subproblem, same subproblem, we reuse the calculated answer. That's all. We are not going to solve it afresh. Okay, no? As a new problem. So that means if there are overlapping subproblems, then what is that we are going to do? We are not solving it more than one time, even if there are overlapping subproblems also. That means what is that we are ensuring each distinct subproblem we solve it only once. Is solved once. Is solved once. That's all. No repetition. Each distinct subproblem is solved. Each distinct subproblem is solved. Each distinct subproblem is solved is only once. If that is the case, total how many subproblems we have in this case? N plus 1 subproblems are not, including original problem. Total number of problems total number of distinct problems we can consider it as, though I have used sub, total number of distinct problems we have here is N plus 1. Total number of distinct subproblems, is it clear? N plus 1 when N is input. Is that correct? Is that correct? Now, what is the relation between number of distinct subproblems versus total number of subproblems? So in case of Fibonacci recursive function, which we saw in the previous slide, what is number of distinct subproblems? Number of distinct subproblems?
N plus 1.
N plus 1. N plus 1. How many subproblems we are solving? How many subproblems we are solving? How many subproblems we are solving here? Can you say that it is roughly
2n plus
1 plus root 5 by 2 whole power n approximately? Is that correct? 1 plus approximately 1 plus root 5 by 2 whole power n. That's what derivation, no? Here almost we calculated that only, no? 1 plus root 5 by 2 whole power n. Number of subproblems we are solving here. That's what this analysis indirectly counts this also, no? Number of recursive calls made. It is roughly 1 plus root 5 by 2 whole power n. That means number of distinct subproblems is n plus 1. Number of subproblems we are actually, total number of subproblems we are solving is 1 plus root 5 by 2 whole power n. That means what does it mean? What does it mean? What does it mean? Number of distinct fruits we have is, say, 5. Total number of fruits we have is 28. That means what? That means what? Number of fruits we have is 5. Number of distinct fruits is 5. Total number of fruits we have is 28. That means what? Some variety. Okay, some variety. It is more than 1, no? Is that correct? Number of distinct fruits is 5. Apple, orange, banana, say watermelon, say muskmelon. You know, this is 5 varieties. Total 28 fruits we have. This is distinct, 5 distinct. This is total number of distinct. That means what? Some variety it is more than 1 or not, or maybe multiple varieties more than 1 or not. Is that correct? Is that correct? So similarly here we have n plus 1 problems, distinct subproblems, but number of problems we are solving, this is total number we are solving. Total number of subproblems solved in this case. Solved is this much. That means what? Some subproblems they are solved more than once or not. Some subproblems they are solved more than once or not.
Yeah, they are called overlapping
no.
problems.
This example, I think this is the some subproblems are solved more than once. Now question is, if each problem is solved only once, each distinct subproblem is solved once. If each distinct subproblem is solved only once. If this is done, if each distinct subproblem is solved only once, what is the total time our algorithm is supposed to take? What is the total time our algorithm is supposed to take?
One plus root 5 by 2 power n.
That okay, if each distinct subproblem is solved only once, then
n plus n
total time by our algorithm, we can say that it is not more than n plus 1 times maximum time for any subproblem. Can we say something like this? Maximum time for any subproblem. Is there any doubt in this? If each distinct subproblem is solved only once, then total time taken by our algorithm is not more than n plus 1 into maximum time for any subproblem. Any means any one subproblem, that is no. Is that okay? So what is cost of these 5 distinct fruits? Can we say that less than or equal to 5 into cost of maximum fruit among 5? Or is that okay? We have 5 different varieties of fruits. I can say the total cost is not more than 5 times whichever is costlier here. One may be 10 or 20, one may be 10, one may be 5, one may be 40, okay, one may be 35. Now, can we say that this cost is not more than 5 into 40? Is that correct?
Yes, sir.
Simple. No? Only this example you try to correlate. Okay, no? We have 5 distinct fruits. What is the total cost of these 5 fruits? It is not more than 5 into what is maximum here. One fruit is okay, watermelon. It is 40 rupees. So we can say that it is not more than 5 into 40. Is that correct? I'm not saying exactly. It is not more than that. Is upper bound is 5 into 40. Is that correct? Is there any doubt up to this? Is there any doubt?
So in this case, can we say order of growth of this particular algorithm is n plus 1 or less
But
than or equal?
we don't know what is the maximum time for any subproblem. I will come to that. We can say that the minimum order of growth is n. It is definitely not going to be less than n. But once you know what is this value also, what is maximum time for any subproblem, then easily we can say what is the total time it takes. What is maximum time for any subproblem? No, this value is known. Automatically, we can say that without even knowing that algorithm, what is the algorithm, we can easily say what is the time it takes. No, is that correct, sir? See, if you know what is maximum time any subproblem takes, based on this, we can say that total time by our algorithm is less than or equal to n plus 1 into this. Is that correct? Is that
Yes,
correct?
sir.
Okay. Now let us go back to our algorithm. Here, if we know what is answer to Fibonacci of n minus 1, what is answer to Fibonacci of n minus 2, what is the time it takes to get answer for Fibonacci of n? If you know whatever subproblems which are required to solve it, immediate subproblems, that answers are available with us. What is the time it takes to get answer for Fibonacci of n? Fibonacci of n minus 1 answer is with you. Fibonacci of n minus 2 answer is also with you. Immediate subproblem answer is with us. What is the time it requires to get answer for Fibonacci of n?
Addition of these two.
Only one addition operation we need to perform. No? That means if this answer is available, this answer is available with one addition, automatically we'll get answer for Fibonacci of n. Is that correct? Is that correct? That means if already if you know the immediate subproblems answer, immediate subproblem answer, to get problem for to get the original problem answer, we can do that in order of one time or not. One addition means it is theta of 1 only, no? Theta of 1. If we know subproblems, immediate subproblem solutions, the actual problem answer can be obtained in theta of 1 time or not. Are you? No, don't think much here. If someone has already given what is answer for Fibonacci of n minus 1, someone has already given what is answer for Fibonacci of n minus 2. Is it possible to get Fibonacci of n in theta of 1 time? That is constant time.
Yes, sir. Yeah, it is a straightforward addition.
This is straightforward addition.
Yeah.
Only 30 theta of 1 time we can do. No. So
Yeah.
now same way here, if you know, if all subproblems answers are available with us, to get immediate subproblem answers are available with us, to get a problem whose solution for its actual problem, is it possible to do it in theta of 1 time? In this case, that means what is maximum time for any one subproblem? Can we say that it is theta of 1, provided provided
Solutions are available.
its immediate sub-problem solutions are available. Its immediate sub-problems solutions are available under this condition only. Otherwise, we need to calculate this, no? Okay. If we know that its immediate sub-problem solutions are available, is it possible to get answer for Fibonacci of n in theta of one time? Is it possible to get
Yes,
answer
sir.
for
Yes.
that in theta of one time or not?
Yes, sir.
Yes, yes. So that means now, okay, we always ensure that its immediate sub-problem solutions are available. That means whenever I am calculating f of 2, I ensure that f of 1 answer is with me and f of 0 answer is also with me. Whenever I am calculating f of 3, we ensure that f of 2 is available, f of 1 is also available. Whenever I am calculating f of 4, I ensure that f of 3 answer is already with me, f of 2 answer is also with me. Whenever I am calculating f of 5, we ensure that f of 4 answer is there as well as f of 3 is there. In this way, can we obtain f of n in theta of one time? Theta of one time, provided f of n minus 1 is there and f of n minus 2 is there? Yes. Yes. Okay. Is that is this point clear? Then what if each distinct subproblem is solved only once, then what is the total time of any algorithm which does this is supposed to take not more than n plus 1 into theta of 1? That means it is big O of n only. Is that correct? Now the same Fibonacci sequence recursive algorithm, that is recursive algorithm for finding nth Fibonacci number. If someone ensures that each distinct subproblem is solved exactly once, and before solving a problem, its immediate subproblem solutions are available, it can be done in big O of n time or not. It can be done in big O of n time or not. Is the point clear? Is there any doubt here?
Sir,
Sir, is there any doubt, sir?
no doubt, sir.
Okay. 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 So please, all of you read what is the definition of overlapping subproblems. What is definition of overlapping subproblems? That's what we discussed. No, what is definition of overlapping subproblem? Is the definition of overlapping subproblem clear?
Yes, sir.
Okay. So now, yeah, finally, f of n we need to calculate. F of n we need to calculate. Okay, now assume the same example I am talking about. F of n, or say n equal to 5 means f of 5 we need to calculate. This we can do it in two ways. One is first I'll calculate f of 0, next I'll calculate f of 1, next I'll calculate f of 2, next I calculate f of 3, next I calculate f of 4, next I calculate f of 5. If I calculate it this way, okay, no, but bottom up. Okay, no, this is bottom, that is up. Bottom up fashion from f0 to f5, in general up to fn, in general fn. Okay, if I follow this way, this method, before solving f of 3, its immediate subproblem solutions are available with us or not? Its immediate subproblem solutions are already available with us or not?
Yes, sir.
So before calculating f20, f18 and f19 are already available with us or not?
Yes, sir. They are available.
Automatically available. No? So before calculating fn, Fn minus 1 and Fn minus 2, are they available with us? Correct? No. This is the order. After calculating Fn minus 2, then only we'll go to Fn minus 1. After that only we'll go to Fn. No. Is that correct? So in general, one by one we are going. After 5, 6 will go, and so on will go. N minus 2 will go. N minus 1 will go. N will go. So before solving this answer is already with us. This answer is already with us. We will add that. We will get answer for F of n. Okay.
So if you follow this bottom-up approach, it would be an iterative solution rather than recursive, right?
Okay. Oh, method you are talking about. Oh, okay. That we can do it in what is that non-recursive way, iterative way.
Yeah, fine.
So this is one way of doing. What is the other way of doing is, I can start with F of 5. So in order to calculate what is required, okay, F of 4 is required. I'll calculate F of 4. In order to calculate F of 4, what is required? F of 3. Again, to calculate F of 3, what is required? F of 2. Again, to calculate F of 2, what is required? F of 1. To calculate F of 1, what is required? F of 0. So that means what? From top, I am starting and I am coming towards down. This way also, from start, I calculate F of 5 I want. Okay, for that I require F of 4. So I try to calculate F of 4. Again, to calculate F of 4, F of 3 is required. F of 3 is required. We calculate F of 3. F of 3, F of 2 is required. F of 1. Now again, F of 0, F of 1 directly we will get. To calculate F of 2, what is required? F of 0 and 1 both are already there. So we calculate this. F of 3, F of 2, F of 1, we calculate this. F of 4, F of 3, F of 2 already calculated. No new recursive call, we calculate this. Similarly, F of 5, F of 3, F of 4, we calculate this. This is called top-down approach. Top-down approach or top-down method. This is bottom-up method. So either top-down or bottom-up. What is our goal? What is our goal? What is our goal?
Solve the distinct problems.
Ensure that each distinct sub-problem is solved. Each distinct sub-problem is solved.
Only once.
Exactly once. Thank you, sir. Exactly once. Whether top-down or bottom-up. What is our main idea? We are ensuring that each distinct sub-problem is solved exactly once. Exactly once. One we can do it. One is top to bottom. The other one is bottom to up. Bottom up, that top-down standard technology. Okay. Now, if you follow either top-down or bottom-up, what is the time it is supposed to take? Our algorithm. That is any algorithm for finding nth Fibonacci number. What is the time it is supposed to take based on the given recurrence?
Big O of n.
That is less than or equal to n plus 1 into maximum time for any subproblem. What is maximum time for any subproblem? Provided its immediate solutions are there, theta of 1. That means it is supposed to take only order of n time. So now this algorithm also is order of n. Even this algorithm is also order of n. Is that okay? Next question is how to do that. In bottom up, I start with f of 0, then I'll go to f of 1. Next, I'll go to f of 2, f of 3, f of 4, f of 5, like this. This way, this fashion I am going. Here, do I need to remember what are the subproblems I have already solved? Is there any question of encountering the same subproblem one more time?
So we should manage a storage space where we need to put all this subproblem solution. So whenever we are going for solving any problem, subproblems, we need to first look at it whether it is solved or not. If it is not, we will solve it and put the result there.
So that is in bottom up, either in bottom up or top down. What is that we need to ensure? What is that we need to ensure?
Order of.
That means first in bottom up, in at least top down, no, automatically that recursion takes care of what are the subproblems. In bottom up, what is the order in which we need to solve the subproblems? This is most important step. What is the order in which we need to solve subproblems. Okay, we'll come to this point later after solve subproblems. This is important. Okay, this is important. Okay, we'll come to this. Now, either top down or bottom up, it is supposed to take how much time? Order of n time. For that, we need to remember what are the subproblems which are already solved, what are the subproblems which are not solved. For that, some additional space is required. That means some table kind of thing. If we maintain this table means it is an array or whatever we call. Okay, what for this table we are using? What for table we are using? What for we are
Storing the result of subproblems.
Distinct subproblems.
Okay, not to solve same subproblem again. To ensure that we are maintaining a table and that table contains one entry for each distinct subproblem. One entry for each distinct subproblem. Each distinct subproblem, one entry. Okay? Not to solve same subproblem again. This is our goal, no? One entry for each distinct subproblem. One entry for each distinct subproblem. Is this correct? That means this is table means it is memory, no? Some memory is required here. What for this additional memory is required? To keep track of the subproblems which are solved and which are not solved, or to distinguish between solved and unsolved problems. Okay. Now, one way of doing here, what is that it is happening? Initially, we maintain a table. Say Fibonacci of, this is our table. This is Fibonacci table 1 to n. This is array 1, 2, and so on. This is say n. Initially, all values I'll make it infinite. That means what? All are unsolved. All are unsolved. All are unsolved. But we know that f of 1 is okay. This is 0 to n. F of 0 also we require, no? This is 0 to n. We know that f of 1 is 1. F of 0 is 0. These two values I'll replace infinite with 0, 1. F of 0 equals 0, f of 1 is 1. Is that okay? Now among n plus 1, how many are solved? 2 are already solved. They are nothing but initial conditions, no? They are nothing but initial conditions. 2 are solved. How n minus 2 entries are infinites. Infinite means that is the symbol I am using to denote not solved. Not solved. Is that correct? So this is one table we are maintaining an entries. Now we call actual algorithm. We call actual algorithm. This goes here. First it checks if Fibonacci of n is not equal to infinite or not. What does it mean? What does it mean? What does it mean? What does it checks?
Already it is complete.
Already solved or not? Already solved or not? Already solved or not? If yes, retrieve the value. Okay, no, get the value. That means no. Okay. If yes, directly get the value. That is, if now it will be there in the nth position, that value we get. Otherwise, we call distinct Fibonacci of n minus. So this is the name. Distinct means each distinct subproblem we are going to solve only once. That's why I have put this name, distinct Fibonacci. Okay, distinct Fibonacci. N minus 1. So this is one recursive call. It gives answer for n minus 1. This gives answer for n minus 2. After that, that value I am storing it in temp. This temp value is nothing but actually our Fibonacci of n value, no? That value we store here. We store here. We keep doing like this. Okay, instead of n, if you are confused, let us put it as some I. Our function call will be n here, so that it gives answer for n. Answer for n. Is that correct? Is the different? Why I made I? Is it clear? This is recursive call, general call function. Here, whenever we call with n, it gives nth Fibonacci number, Fibonacci of n. What is the time this algorithm takes? What is the time this algorithm takes? In place of I, n is supplied. What is the time this algorithm takes? What is the time this algorithm takes? What is the time this algorithm takes? You do not even think about this algorithm. Already, what is that we have learned? If each distinct problem is solved only once, only
Order
once,
Below of n.
number of distinct subproblems is number of distinct subproblems is number of distinct subproblem time calculation. Number of distinct subproblems is n plus 1. Maximum time for any subproblem is theta of n. So therefore, total time is theta of n. Is that correct or not? See, the problem which was 1 plus root 5 by 2 whole power n, it has become theta of n. Drastic change, no? Drastic improvement. It is at the cost of this. What is this? Some additional memory. How much memory? Theta of n amount of memory. Why? Because n plus 1 entries. That's why n plus 1 means theta of n memory. Additional memory is required. Is that okay? Is that clear? Is this a top-down approach or bottom-up approach? Is it a top-down approach or bottom-up approach?
It is top-down.
It is top-down. It is top-down approach. Top-down approach for what? For ensuring that each distinct subproblem is solved only once. Now the same thing we can do it in bottom-up method also. Okay, sorry, directly I have written this. One more algorithm Fibonacci of n. Step 1, for example, you take Fibonacci of 0 equal to 0, Fibonacci of 1 equals to 1. You can similar to whatever we discussed for I equal to 2 to n. What is that we can write? Fibonacci of I equals to Fibonacci of I minus 1 plus Fibonacci of I minus 2. Next, written Fibonacci of n. Is that correct?
Yes, sir.
Yes. Okay, now here, is it a bottom-up approach or top-down approach? This algorithm? This is also distinct.
Bottom.
This I call it a distinct Fibonacci 1. It is bottom-up approach, no? It is bottom-up. Usually we can see that this algorithm running time is how much?
Theta of n.
I equal to 2 to n 1, which is n minus 1, which is theta of n. Is that correct? Time is theta of n. It is same as what we expected. But what is the space it takes? Fibonacci of 0, Fibonacci of 1, Fibonacci
Theta
of 2,
of
Fibonacci 3. That is n plus 1 units.
Hmm.
That means it is theta of n. Is that correct? Now the same algorithm here. What is the change? What is time here?
Theta of n.
Theta of n. But what is the space?
Constant.
It is constant. Theta of n. There is no additional space. No. A, B, C, I. 4 units. 4 units means it is independent of I. Independent of n. Is that correct? It is independent of n. Okay. So this is called bottom-up method. Is it bottom-up or not? This one? Is it bottom-up or not? This is also bottom-up. Where we are ensuring that each distinct subproblem is solved only once. once. Is that okay? Okay. So this is order of n algorithm, order of n time algorithm. In fact, in literature, okay, no, I am not going to do that. There is also an algorithm which runs in only nth Fibonacci number. We can do it in order of log n time also. Order of log n time also. Okay. Order of log n time also. There are algorithms. Okay. There are algorithms. Is it clear up to this? So far, what is that we have done? Based on the recurrence relation, we can easily give a recursive algorithm, and that recursive algorithm, the amount of time is more, then we get a doubt, why is it taking so much amount of time? Then we will see what are the number of distinct subproblems and total number of subproblems which we are solving in that problem. If the total number of subproblems is very much high when compared with the total number of distinct subproblems, then we get doubt like, okay, there is some repetition, same subproblem we are solving again and again. Then what is that we can do is, we ensure that each distinct subproblem is solved exactly once. That we can do it in either top-down method or bottom-up method, top-down method or bottom-up method. Then what is the total time our algorithm takes? What is the total time our algorithm takes? It is equal to not more than number of distinct subproblems into maximum time for any subproblem, maximum time for any subproblem. That is the total time our algorithm takes. Next, is it clear what is overlapping subproblem? How to ensure that each distinct subproblem is solved exactly once? Now let us see the definition of what is optimization problem. All of you must be knowing what is an optimization problem.
Sir, can we start new topic after the break?
Okay, sir. Okay. Now we will have break for half an hour. 6:30 again we'll start. Okay, thank you.